Let's take a look at three-dimensional trig. So problems in 3 dimensions. And it can be tough sometimes because of the way pictures can be drawn to actually see the triangles. So I find it useful to redraw the different faces in 2D, and it just becomes a standard 2D problem then, and we know how to do those quite easily. But sometimes you need to draw triangles that are not actually in the diagram that you're given. Then we'll do some examples, you'll see what I mean. Pretty much there's 2 situations in 3D. It might be you're trying to find the angle between a line and a plane. So let's look at this for an example. We've got a cone, diameter 18 in the base there. Slant height of this cone is 15. We want to find the angle that that curved surface area makes with the base. So the first thing we'll do is we'll drop a perpendicular from any point on the line. Now which line? Well, if we're talking about the curved surface area, it could be any, for want of a better word, edge. Of course there's an infinite number of edges when you think about it in a circle, but I can use this one here that I've labelled 15. If I drop it straight down and it meets the plane, the circle at the base there, at the diameter, then we would join the point of intersection to the point where the line meets the plane. Well, in this case, it's already drawn because I've got the diameter marked in. But we've created ourselves a right angled triangle there. And that angle here that I've labelled theta, that would be the angle then that curved surface area makes with the base. The radius, of course, is half the diameter. Now I've got a very simple trig problem to solve. Cosine of theta is 9 on 15. We get 53 degrees. Okay. The other situation we could get is actually 2 planes are meeting each other. So I've got a tetrahedron here, side length A, doesn't really matter what I call it, just all the sides are the same length. Find the angle between 2 adjacent faces. Okay, so now I need from a point on the line of intersection of the 2 planes. Well, let's say I'm looking at the plane ABC and the plane BCD. BC would be the line of intersection of those 2 planes. Now I could pick any point I like and draw perpendiculars, but there are sort of logical places to pick. Now when I'm talking about the base of this one, it probably makes sense to go perpendicular, so I go through the vertex on the other side. And so, well, similar with the triangle ABC. So I've got that one going up to A, that one going across to D, and I've created now a 2-dimensional triangle that'll allow me to find the angle, because the angle between the 2 planes will be that one in there, angle AED. So where the 2 planes have met. This is one where I think I'll redraw that triangle so I can see it properly in 2 dimensions. That angle's theta. We know the side length is A. That has not really enough information as that stands. So if I draw another triangle, the base, the actual base itself, and mark in the same things, again we know the side length is A. Because it's a tetrahedron, all of these triangles I know are equilateral triangles. So that angle must be 60 degrees. I can therefore work out AE and then use that information in the first triangle. AE, I know it's going to be A times root 3 on 2 because I've got our standard 30-60 triangle there. I know the sides are in the ratio 1 to root 3. Or of course I could have just used trig and said A over, oh no, it'd be the other way around, wouldn't it? AE over A would be the sine of 60, wouldn't it? Be the sine of 60. Now to solve this problem, I'm actually going to have to use the cosine rule to do it. Because the nice thing is I know AE must be the same length as DE, because all of these triangles are congruent. It's a tetrahedron. So cosine theta then will be 3a squared on 4, which is our root 3a on 2 squared, plus, and the other side's also the same, so 3a squared on 4, minus the side squared opposite the angle I want to find, so minus a squared, over 2 times those sides. All of that cancels down. Eventually I get the cosine of theta is 1/3. And so I know I've got theta is 70 degrees 32. Here's an old HSC question. Now you'll notice it's an extension 1. 3-dimensional trig used to be in the extension 1 course. It's now in the 2-unit course, something that came back from Extension 1 into 2-unit. So here we go. A surveyor is standing at our point A down here. That's due south of our tower, OT. Angle of elevation, 45 degrees. Surveyor then walks due east 100 metres, and she measures the angle of elevation there. It's now 30 degrees. The question started off simply saying, well, what's the length of OB in terms of H? Well, let's find a triangle where OB is in it, and we've got other information. H would be good, and there's the triangle I chose, triangle BOT. The angle of elevation was 30 degrees, so it's just a simple little trig question. OB on H is tan 60, H tan 60. I suppose you could go even further because we know what tan 60 is exactly. Yeah, so we could have said it's root 3H, but there it is, it's in terms of H. Okay, show that H is 50 root 2. Let's draw some more triangles. I had this other one. We do know this angle is 45 degrees, so we've got the angle of elevation 45. I'll tell you what that tells me. This triangle must be isosceles as well. So OA is also H. Now, was that useful in how I solved this one? Now I've got another triangle I can draw that has H in it, because now I know that OA is H. We just worked out OB was H tan 60 and AB we were told were 100. Okay, I should be able to use Pythagoras on this one. So H squared plus 100 squared, H squared tan squared. Eventually, playing around with it. No, not there yet. Oh, still not there. There we go. H is 50 root 2. So we've got part 2. Calculate the bearing of B from the base of the tower. So I'm now looking at the base, and I've put a compass at O because we want the bearing of B from O. So the compass is there. We have now worked out that OA is 50 root 2. We know AB is 100. The bearing, start at north, go clockwise. That's the angle we're trying to find, angle NOB. All right, what else do we know? Well, the tan of angle AOB, if I can find that angle, I can subtract it from 180, we'll get the bearing, is 100 on 50 root 2. So that's 54, 44. The bearing will be 180 minus that, 125, 16. Okay, now 6C.